Yeah, because all I did was I copied and pasted. Yeah, you can see exactly the same. Because you can make a case. Well, this has an upward swing. It's not a line, but I could model it with a line, but I could also model it with a quartic function. All right, so let's actually talk about what a quartic function looks like in general. All right, so quartic functions are W-shaped graphs in some capacity. You know, it doesn't have to be a perfect W. It could be a wonky W, or it could be M, you know, the reflection of that. So you could be looking at something like this. Quartic, yep. Just like this. So you could model this with a quartic function as long as you could fit a curve that has these characteristics in it to that data set. So the way it would look, because I can see that it has a little bit of a tail here, then it comes up, and it also has a little bit of a tail here, and then it comes back up again. All right? You could put it there. Maybe you can, if you want, you can kind of shoot it upward a little bit. Have it go through the body of the data set. All right? But you could also, like we were saying, you could also fit a straight line through it. You know, it's a question of which is going to be more appropriate contextually, all right, based on the problem that we'll be dealing with. There should be I wanted to change the characteristics of this. Oh, here it is. No. That's the one, yeah. Let's make that popping red. Good looking graph right there. Right, but it has to have the W or the M characteristic. Yeah. Yep.
That's fine.
Yep. Perfect. So quadratic, so I'll take it back from the beginning here. The quadratic function is your parabola. So just thinking back to algebra, trig, U-shaped or a reflection of that. I think that one's a little bit more obvious because there we go. The cubic function typically looks something like this, or the rotated version of it might look like this, or it could be going downhill. And so looking at those graphs, you could see how a curve might fit. Kind of like an S curve. Now, if you're worried about how are you going to remember all this stuff, well, you should know it already from algebra class. And if you don't, you fail. Now, I mean, in an ideal world, of course, you'd remember everything that you learned in every class. I would love for that to happen. But that's not always the case. For some of you, this is like, oh yeah, we did this last semester. And some of you are like, I've never seen this before. The calculator is going to figure all this stuff out for you. All right. It'll even give you the name. So this is more like, I don't want to say public service again, but it's kind of along those lines. It's like you're just learning the nature of the graphs for learning's sake, rather than I need to memorize this, okay? Which is a good thing. Exponential graphs, you'll find that these are one of the more useful types of functions in the real world. Because when you talk about interest rates, biological growth, even in some cases, chemical reactions, They follow exponential relationships. Physics, there's something called Newton's law of cooling. Regardless of what the name of it is, I can tell you that when I made my coffee this morning, I put the cup in the Keurig, I put the little cup in there, and then I brewed that bad boy up. I would have loved to take a sip out of my coffee immediately, but I would have like roasted the inside of my mouth, so I did not. I know that I have to wait a certain period of time before I can drink my coffee because I like it black. All right. So the question would be, how long would that period of time be? Well, I'm not going to sit there and solve a mathematical equation to figure it out. I just know like a good 10 minutes or so gets the job done for me. All right. People have different tolerances, but common sense tells you that over time, we have something that's extremely hot, it's going to cool. And it's going to cool, and eventually it's going to stop cooling. Right? It's going to level off at a certain temperature. It's not going to just keep cooling and become like a block of ice. Right? Like that would be interesting, I guess. But eventually it's going to level off at room temperature, following a path like this. All right? It's going to have a dramatic decrease in temperature early on, and then its rate of decrease is going to slow until eventually it hits room temperature. That's all Newton's law of cooling is saying, right? Except there's like really fun calculus involved in solving equations related to it. But common sense-wise, it's pretty straightforward, right? But you could think of probably 1,000 different examples. You know, if you started now, you could, without interruption, think of straight up 1,000 different examples of that in real life. That curve happening in real life, one way or the other, going up or going down, without even taking a break. You know, so very, very practical. Also practical is the natural logarithmic. Right, it's a graph that looks like this. Right, so it's basically, honestly, it's like out of the two graphs I drew here, it's basically the one variation of these graphs that I didn't draw. That's the natural logarithmic. There could also be reflections and different variations on it. But and here this looks like a linear function, right? But depending on the context, I could fit a natural log into it. All right. So let's go the other way. Instead of taking the coffee out of the Keurig, maybe I take an ice pop out of the freezer. Right? And I put it in a bowl. I had every intention of enjoying that ice pop, but I forgot. So it's sitting there on the table. It's going to increase in temperature. The most dramatic increase will be early on, and then eventually it's going to level off to room temperature. It's going to be a puddle, but it'll be a puddle at room temperature. Another example, right off the top of my head, would be the growth of a person or any living creature, I suppose. You know, it's like you don't grow infinitely. You don't grow in the form of a linear function. Otherwise, I'd be like 1,000 feet tall right now. Right? You grow dramatically early on. Like you think. I mean, I don't know how many of you have kids, or I mean, I'm sure at some point you've been around them, those people. They start off like this big, and then a year later they're this big. And you're like, how did that happen? They doubled in size in 1 year. Like, actually doubled in size in the period of 1 year. That's crazy. That would be like me now, and then you meet me next year, and my head is above the ceiling. Like, that would be the rate of growth. That's why I was saying I'd be like 1,000 feet tall, because every year my height would be doubling. That's insane. All right. So at some point the height has to level off, and that's where a natural logarithmic function comes into play.
So natural logarithms, they only go up?
They can go down, but we're only going to focus on the cases where they go up, because we can do what we need to do with the exponential functions. The none situation, I think that probably doesn't need much of an explanation. I'll give you a small one, though. There's no pattern whatsoever. It's not going to fit a line. It's not going to fit one of these nonlinear plots. They're just data points that are scattered all over the place. So before, when I was talking about context, I was saying, you could have two data sets that don't seem to relate to one another, but mathematically they do. Like you get the numbers to say there's a relationship here, but common sense tells you that no, there's no relationship there, right? This is the other way around, where because at some point you're prompted to make a plot. You're thinking, I think there's a relationship between these two data sets. Let me see what that looks like, and you make your graph. This is the other way around, where common sense is telling you that there is a relationship, but the data is not bearing that out. Right? The data is all over the place. You can't get it to work mathematically. You can get it to work in terms of common sense, but the math is not working out for you. All right, so we'll learn how to handle those kind of situations too. All right, but like I said, I don't think I'm lying. This is stuff that you could apply immediately. You use it for gambling, stock market, which is gambling. You could use it. They use it for medical purposes. They just don't sit there and use the actual function equations, but there is medical applications of it. Because if you're talking about the you just I mean, I take medicine every day. You take your medicine in the morning, and you know how it says like on some pain relievers, for example, it says take one pill every 4 hours. It's like, where do they come up with that 4 hours? That comes from the research. It's like the research. The research tells us. That's also one of my pet peeves. I don't like that. What research showed? I think you're lying. You're just saying the research. But anyway, what they do is they actually conduct the research and determine the rate of saturation of the medicine in your bloodstream. All right, and so once they figure that model out, it essentially ends up being an exponential function. All right, and so that level of saturation declines over time. And so when you start thinking about things like overdosing, it's like, well, what is the prescribed amount of medicine? X. Well, we don't want to go over that. So if you were to take that second pill before 4 hours have elapsed, you still have a sufficient quantity in your bloodstream so that when you introduce the next pill, that spikes it up over the acceptable amount. All right, but that's all determined by that exponential function. It's a rate of decay. All right, radioactive decay, carbon dating, and things like that. It's all the same concept. Half-life. I mean, my doctors talk about that all the time. They're like, the half-life on this medicine. That's after they ask me what I do for a living. Then that's like the license to talk to me in terms of like the real terms. But these are important concepts. And so what we want to do is figure out the math that's going to allow us to interpret the context of the situation. We have a sense of the context. That's why we're collecting the data to begin with. The math is going to help us either confirm or refute what we think in terms of a hypothesis, and then after that we'll draw a conclusion. You see this nasty formula here? That's gross. Yeah, it's built into your calculator, so you don't have to worry about it. It's a recurring theme of the course. It's like, here's an ugly formula. You're never going to have to use it because the calculator does it for you. So I used to make my students do this formula. I think I might have said this about another thing too. That's also a recurring theme. There's a lot of things when I first started teaching that I did not know that the calculator did. And so I was like, well, you got to use the formula. How else are you going to do it? So we did it. And one day somebody was like, so the calculator does that for you, right? And I'm like, of course I do. I find value in learning how to do it by hand. And so that's what we're going to do. And then the next semester I'm like, so I don't know why anybody would do it by hand. You do it on a calculator. So only an idiot would do it by hand, And so that's the backstory on that. Yeah, so this is a lovely formula, and I gotta tell you, I did not know where this formula came from myself until I started teaching Calculus 3. So not even as a student in Calculus 3, as a teacher of Calculus 3, that's when I learned where this formula came from. So just reflecting back, like 18 years ago, there was no valid reason why anybody should have been doing this by hand. All right, you're not gaining anything from it because you're not learning anything about the structure of correlation through the use of the formula. All we care about is the number. So that brings us to this. Oh, that's the thing. All right, typo opportunity for somebody. All I need is whatever the stage is, and then the words r squared, so the r squared table. You can just write out r squared. We're going to make the table together now, but I've been meaning for a solid decade to put that table in here, and I keep forgetting. So r squared and type. All right, so we're going to have 1.75. Let me move that over a little bit. I'm basically going to reproduce the first 3 rows with a slight adjustment. I'm boxing the wrong thing. Yeah. That's a 1. Yeah. It's a poor quality 1. The last row will be a new row. All right, so the first 3 rows are the same on the left. 1, 0.75 to 1, 0.5 to 0.75. But the fourth one is going to be 0. Oh, I forgot the R. Sorry. That's a Saturday morning mistake. Zero is less than or equal to R, which is less than 50. 0.5. Right.
With a non-section, right?
Yeah, then we're going to call that no significant correlation. If it's exactly equal to 0, the R value, or the R squared, then it's exactly none. But it's really anything close to 0 that shows that there's no significant correlation. Because there's still a correlation, it's just not a meaningful one mathematically. And again, we're talking about the math side of things, not the context side of things. Okay? If we're talking about context, you might look at it and say, well, there's a relationship. The weight of the car and the fuel economy are related to one another. It's just this data set is not bearing that out. All right. So a natural question on your end would be, all right, cool. How do we get that R squared value? All right. We'll get to that in a minute. All right. The definition of R squared in percent form is a percent of variation in the Y variable that can be explained by variation in the X variable. All right. It's phrasing-wise, a kind of like an iffy sentence, but if you kind of break it apart piece by piece, it starts to make a little bit more sense. You're talking about variation, which is really deviation from the average. All right, so how far away you are from the average value. All right, so we're talking about the percent of deviation in the y variable. So that's, forget x and y. There's two variables. So the amount of deviation in one variable is going to be explained by deviation in the other variable. It's just how much of it will be explained by. All right. So think of it this way: if there is a cause and effect relationship, you would think that any change in one variable would cause a change in the other variable. All right. So if I go with the height weight analogy, the cause and effect would be the person grew by a foot. That caused their weight to grow by 20 pounds. More, I don't know what the scale is. So maybe 50. But that caused the other thing to happen. All right. Now maybe there's lurking variables in there, but you could show a causal relationship. You would expect the value very close to 1 because you're talking about maybe not 100% of that weight was associated with the height change. So you'd look at it and say, did every like teensy tiny millimeter of that 1 foot of growth correspond to every like teensy tiny gram of increase in weight? No. Right? So maybe only 75% of the weight was associated with the height growth. Maybe the other 25% was the fact that the person decided that they liked Popeye's chicken in New Rochelle. Not New Rochelle, sorry, Portchester. I always get them confused. For whatever reason, I get those two cities confused with one another. Yeah, I didn't know that there was a Popeyes in the area. And then all of a sudden I knew there was a Popeyes in the area. And that changed things for me. So, it's good. And I also didn't think I liked the spicy, but I like the spicy. I like the spicy a lot. Probably a little too much. Alright, so, grew a foot, gained, let's say, 30 pounds, but maybe 10 pounds of the weight gain was for something other than the height. That was for diet change, or maybe it's the lazy time of year where you stop going to the gym, stop exercising, you put on a couple pounds just naturally, but at least some of that weight gained would be related to the height gain. All right, that's what this is talking about. The R squared will tell you what percent of that weight gain was related to the height gain. All right, mathematically. Now, again, there's the common sense part of it, but generally speaking, the math is very reliable. Okay. We could also come up with something called a linear regression. Unfortunately, this is one of those terms I don't think that actually defines itself. I mean, the linear part, that's fine, but this is talking about fitting a line to a data set and coming up with the best line that could fit a data set. Now, when I was first learning about this, it was plot the points, bunch of points, grab a ruler, and all right, that feels right. Right? So that's your line. Come up with points on the line and write the equation. All right? We don't want to do that, obviously. That's not very accurate. The calculator will determine, using these lovely formulas, the line that best fits the data set. All right? What it does, actually, it's another Calc 3 thing, which, I mean, it's like, what does that mean? Conceptually, what it's doing is minimizing the distance between the point and a line. So it fits a line, and then basically the process kind of wiggles that line around and recomputes how far each point is away, and then gets those totals and then just keeps moving it until it comes onto the perfect placement of the line where those distances between the points and the line would be the smallest in total. All right. So it's kind of weird to think that a mathematical formula can do that, but that's the power of calculus. The benefit is, well, we get the benefit of that in this class. Okay. So the calculus happened in another class so that we could use it to analyze situations in this class. All right. And that's where the process comes from. And this is the moment of truth for me, where I determine if I remembered to update these steps. I did not. Okay, well, some of this is right. We'll get to the parts where everything's right. So let's tackle an example. I used to have an example here. That I did edit. I'll talk about making predictions in a sec. It's just like I put this in the wrong spot. I don't know why I say. Because this example doesn't talk about making predictions. Well, it kind of does. Yeah, actually it does. I saw percent, and it's a new example. So anyway, but I'll talk about this in the context of the example. So ornithologists, scientists who study birds, rank sparrowhawks in 13 different colonies to study their population. They gather data for the percent of new sparrowhawks in each colony and the percent of those that have returned from migration. All right, so we have the percent of return and the percent of new sparrowhawks. Typo opportunity for somebody? A tab between percent return and the first number, because I think it's probably easy to lose the 5 here. So in example 1, tab. That's all I would need to know what the hell I'm supposed to do there. All right, so we got to type in our information. So we have 2 data sets, so we're going to type it into L1 and L2. Stat edit. I'm going to clear out L1, so again, clear and enter. And then you just start typing. So 74 is the first one, and so on, 66.
Says the name snuff. I don't know if this is like per second and stuff.
Oh no, just stat edit.
Oh, okay. And clear the L1.
And clear the L1. Yeah. And again, just be careful about data entry, because I've already typed in like 3 values incorrectly. All right, so my data's in. So I'm going to walk you through the process in a second. It's slightly more involved than the other kind of calculations that we did, but not in a crazy way. And the trade-off is you don't have to worry about like nasty formulas and doing anything by hand. Right?
You missed the number. Is there a way to insert a number in your...
Yeah, so go to the number that you want to put it in front of and hit second delete, and it should open a field that you can put the number in. All right. So yeah, the process, even using the calculator as a support tool, there would still normally be some algebra involved, and I've taught it both ways. And again, it's the same thing I was saying before. Like I taught it the other way when I didn't know about these tricks. The approach I'm going to show you is to help you avoid having to do algebra at all. All right. The idea is that once you type the data in your calculator, you can come up with your answers without writing anything on the paper except for the answers. All right, that's what I'm going for. All right, if you find yourself solving an equation at any point in this class, you're probably going about things the wrong way. All right, we're not about equation solving here. All right, the calculator does it all for us. All right, so I'm going to quit out of here, second mode. Then I'm going to hit stat, calc. All right, again, calc stands for calculate. So if you need numbers, that's probably where you're supposed to go. All right, we're going to go to option 4, which is linreg. So considering the title of this topic is linear regression, there's probably a pretty good justification for selecting that one. Now, the issue is the phrasing of the question can be a little daunting because, immediately they kind of mess around with you and throw one of the alternate titles of linear regression. Linear regression is also, it's all on the previous page, also known as the least squares regression line, also known as the line of best fit, which I think is the best name for it, because that's the one that tells you exactly what it is. Then there's also the Pearson product moment linear regression equation, which is like, why would you call it that? But this one has actually a pretty good abbreviation. LSRL. It's not like an acronym or anything, but LSRL. Least squares regression line. Let me get rid of those. I'll do it all caps. All right, that's actually the standard statistical abbreviation for linear regression equation, least squares regression line, and so on. So that could be the notation used on the test, right? So if that finds its way onto your index card, it's probably not the worst idea in the world. Right. Why would you do that? Well, that's part of the notation. So
No, LSRL.
LSRL, yeah. So the question could say, use your calculators. Well, regression functions kind of given it away to find the LSRL. And unfortunately, if you ask during the test, what does LSRL mean? I'm going to say, hopefully you wrote it down on your index card because I can't tell you. Right? And the reality is I could tell you, I'm just going to choose not to. But I'm going to say that I can't tell you, by like the people who are in charge of me. So just to make you feel better about things. All right, so we're going to choose option 4, which is going to bring us to a menu. And that menu is going to ask you to input a few things. Now, the default is L1 and L2. We leave frequency list blank. Now, if L1 and L2 are not plugged in for X list and Y list, put them in. Second 1, second 2. All right. We're also going to include an additional step here. All right. And I'll show you why it's important in a second. A brief teaser is that it has everything to do with answering the next 2 questions.
In frequency list, I have L2 or A2
frequency list, leave it blank, so clear it out.
I'll just press here.
Yep.
Not just the ace question.
Yeah, that's fine. So store regression equation. What we're going to do is hit alpha, which is right below the second key. Trace y1. Alpha trace y1. So if you just hit enter on that y1, you'll have what you need. All right, so I'm going to hit enter. And so what it does is it plugs y1 into the field that says store regression equation.
And that was alpha trace.
Alpha trace, and then select y1. And then you go to calculate and hit enter. And it'll give us the least squares regression line. Now, we are going to have to come up with the correlation coefficient in a minute, but we have to change the setting on our calculator, so I'll show you how to do that. If you have A, B, and then also R squared and R on your display, then your calculator is already set up the way that we're all going to set it up in a sec. But for now, as long as you have these two pieces of information, that's all we need. All right? So this is our equation. Yeah. Right. Right. Oh, interesting. All right, I'll take a look in one sec. Oh, gotcha. All right, so depending on rounding, you might come up with slightly different variations to this answer, but what you want is the most exact form, right? Because exactness gives accuracy, right? So all of these decimal values should be included in your final answer. And in fact, this is what you should produce on paper, just exactly the way the calculator displays it. Because what happens is on the top, they're giving you the equation form. They're saying what the equation is in its most general form, y equals ax plus b. You might better know it as y equals mx plus b, slope and y-intercept. And then they're defining what a and b are for this particular situation. All right? They're saying that we have a slope of about negative 0.3 and a y-intercept of about 31.9. All right? The reason why I say you don't have to worry about putting it actually in equation form is because of what I was saying before. Our intent is to have the calculator do all of the work. All right? So why would I write it in equation form if I'm just going to have the calculator solve equations for me? Right? And I'll show you a little bit more about that in a sec. All right? I do want to go back and talk about these variables. So percent return, we define that as our X list. So that went into L1.
It doesn't give me.
Oh, polar mode. Sorry, wrong. I had it set up for a different class. So it's that. So I'll get you back where you were. stat cal 4. Okay, do the alpha trace, and it's going to work now. So percent return is x, and percent new is y. So it's saying determine the percent return, so determine x, if the percent new, the y, is equal to 25. So it's saying find x if y is equal to 25. All right, that's the interpretation of it. And part C is saying do it the other way around. Find y if x is 90. All right. So part of the challenge, I mean, really, you took a math class that's all about word problems. Like every math student's least favorite part of math class, word problems. So you took an entire course dedicated to the study of word problems. All right. And what's the biggest challenge in word problems? Going from the words to the math. All right. Once you get the transformation from word form to math form, it generally works itself out from there. Because even the interpretation is fine because you made that transition. All right. So understanding which variable applies in which situation allows you to interpret these correctly, which allows you to follow the correct approach. All right. So the first thing that we want to do is find an x given a y. So determine x given a y, sub the given y into the best fit model and solve for x. That would be the by hand approach, which I am anti. How about this? Enter the best fit equation into your calculator. Enter the y as an equation, then find an intersection function. All right, so let's do that. All right.
How do you know X is
Because the first set of data that you type into your calculator is always going to be x. All right. So we have our equation here. The process is telling me to enter the y, the given y as an equation, but also enter the best fit equation into your calculator. It's already entered. When I hit y equals, so just hit y equals, that equation is already there. All right. I could scroll over it and look at, well, there's a lag on this, but you can scroll over if you want. But you could also take my word for the fact that the calculator took the a value here, plugged it in for a, took the b value, plugged it in for b, and then took that entire expression, including the x, and typed it into y1. It stored it in there for you. All right, so that's good to go. The second part is enter the given y as an equation. They gave us y as 25. So as a separate equation, y2, type in the 25. Oh, you just hit y equals. Because it should already be there.
Oh, yeah.
Yeah, the whole equation. And all we're doing is typing the given y value 25. We're putting that in y2. So hit enter, and then type in the 25, and then hit enter again.
Well, just quick question. The thing is that I press y equals and I get in the first row that same thing that you have, but then there's something already in y2, which is x minus x to the third power over 3 plus x.
So just some kind of algebraic, just hit clear to wipe all that out,
Okay.
and then type in the new thing. Okay, so we're going to do all that, but something else that we also have to do is set up the stat plot, right? So that's another little nugget here. So we're going to set up a stat plot. And the more you use the stat plots on the calculator, the more intuitive it becomes. It's just, you know, the first time you started using this calculator, it was like culture shock. You know, assuming the first time you used it was in this class, and then as you use it a little bit more and more, assuming this would be a red flag, assuming that that the, it isn't like the only time you're ever using it is here, like during this period of time, like you're actually practicing with this stuff at home, that would be necessary, right? Because if you're a blank slate every week, then you're going to be a blank slate most likely when you sit down to take a test. So that would be bad, right? So things like the stat plot, yeah, you take good notes. That's a good idea, but then also try it again. Like the problems that we do in class, make sure you try them at home, because otherwise you're going to lose the skills. All right. So I think that's a general, course of action. Most people are familiar with that. I just figured I would say it just to make sure. Second, y equals. Hit enter on plot 1. All right, we have, again, scatter plot. We have a frequency polygon, which we never use. Frequency.
How do I, y equals 25, then how do I just get back to this one?
Second, y equals. And then enter on plot 1. All right, so we have the scatter plot, frequency polygon, which we never use, frequency histogram, which is very important, but not in this case. Then your box plots. The last one we learned about was the normal probability plot, which actually, unfortunately, kind of looks like a line, which kind of might make you think linear regression, but that's not the one we want. So we're going to hit enter, and we're going to go right for the scatter plot. All right, those graphs that we were talking about initially, where we were saying the types of linear plots and the quartic plots and things like that, those were all scatter plots. That's what we want whenever we're dealing with correlation and regression. All right, so I'm going to select that. You'll see that the default is L1 and L2. If it's not listed as L1 and L2, make it say L1 and L2. Because if you don't, you're gonna have a bad day. No, yeah, you'll just have to go back and make an adjustment. You'll get a nonsensical graph, and then you'll have to fix it. So it's one of those things where it's like, okay, it's not a big deal. It's just I would have liked to have those 2 or 3 minutes back. All right. So as always, when we're creating a graph, we hit zoom, option 9, zoom stat. So zoom stat, hit enter. So you have the scatter plot, and you have the line. All right. So the scatter plot and the line that best fits that scatter plot, which is what we came up with over here. Which is great, because now we have the visual to go along with all the computations, because the computations taken out of context, they just look borderline meaningless. You're like, what do I get out of this?
So zoom
And
stat.
oh, sorry, zoom stat. So zoom and then option 9 if you scroll down.
Oh, there we go.
Yeah. All right, so that's a nice visual. Unfortunately, we still haven't answered the question, but we're going to need to do this anytime you have a regression question. So, it's good skills. And also, it's going to help us evaluate outliers and influential points in a set. So, what I need to do is figure out where that y equals 25 line went. Because y equals 25 is a horizontal line. All right, and I don't see a horizontal line on my graph. All right, so what I'm going to do is I'm going to hit window. All right, so this is a thinking step. Every now and then we have some of those, where it's not just like follow the steps in the process, where you actually have to consider the situation and then draw a conclusion. All right. So I'm looking at this window, and if you're not overly familiar with function-related mathematics like domains and ranges and just graphs in general, now it's a prereq for this class, but we all know what that means. It's like, yeah, you need to have taken these classes before taking stat, and then they don't check like a register, and they're like, oh, you want to take Calc 3? Go ahead. I'm like, oh, you haven't taken Calc 1 or 2, but go ahead, yeah, we'll take your money. So, in theory, you completed some kind of algebra class prior to this where you would have seen this, but you never know. That's all I'm getting at here. That y max is giving us the highest y value on my graph. Right? X min gives me the lowest x, x max gives me the highest x, y min the lowest y, y max the highest y. My y has to go up to 25. The calculator is only making my y go up to 22 and a half, roughly. Well, I need it to be bigger. So I'm going to make it bigger. I'm going to use an advanced calculator technique called typing in a bigger number, like 26. That was some high-level stuff right there. Hit clear, or you can just overwrite it. If you start typing, it'll overwrite the values that are there. Clear to give yourself a nice blank slate. All right, so now, full disclosure, in this particular instance, doing it algebraically actually probably would be a quicker approach, but it's for a linear function. All right, and all that means is, well, linear functions are easier to work with. When I throw a quadratic function at you, and I ask you to do the same thing, you'd be spending the rest of your life trying to solve it if you're using an algebraic approach. Right? So we're learning a complicated calculator approach, even in a simple instance, so that when you get to the harder cases, you're okay with it.
Why did you put 26?
Oh, I just needed it to be bigger than the 25.
Oh, so it can't be the 25.
Right. Yeah, because then it'll be right at the top of the screen. Yeah. 25 might be all right, but I want to give a little space on the high side. So yeah, anything bigger than 25, you put 100 if you want. Just don't go too high, because otherwise it'll be compressed all the way to the bottom of the screen. So then after that, you hit graph. All right, so on your calculator, you're not hitting zoom anymore, because once you adjust the window, if you hit zoom anything, it's going to put it back to the settings that it was before you made the changes, which is annoying. So I got the line going through the points, and then I got that. All right, so again, I'm looking for an intersection between these two lines. All right, we're taking a procedural approach here. I don't know where that intersection is, but I know it's not on this screen. It looks like it's to the left, right? So I need more left. So they put, based on this scale, the calculator, the little dude that lives inside the calculator, did all the math, and came up with, in his infinite wisdom, came up with 33.7 as the x min. Based on this picture, I'm not agreeing with that. Now, it's a good window to display the line going through the points, but we need more. All right, so what I'm going to do is I'm going to go back to the window. I'm going to make this value, I honestly, I don't know where it's going to be. Maybe changing it to 20 is fine. Maybe 0. 0 is probably your best bet because we wouldn't expect negative numbers. We're talking about sparrowhawks, birds, number of birds. Negative numbers wouldn't make sense in this context, right? The percent returning and a percent new. So percents always exist if you're talking about discrete percents. So percents representing a quantity, they always exist between 0 and 100. All right. So now if you're talking about growth, it could be more than 100. Like if somebody tripled in height, their growth, like they increased their height by 200%. Right. That's a different story. So there is a place for that, but I'm going to change my window so that the x min now gets changed. I'm going to make that a 0. Now, let's say you decided to change it to 20. You hit graph, they still don't cross, go back into the window and make it smaller, right? So you'll get it eventually. It's just a question of how long it's going to take. So we're going to make this 0 because this is too big. So then I'm going to hit graph again. And now I have an intersection. All right, you can see it right here. Zero, enter, then graph. All right, I'm looking for that intersection. Now, I don't want to do one of these, like, let's do 1, 2, 3, 4, 5, like 25. I want the calculator to tell me where the intersection is. All right?
Trace.
Second trace, option 5. All right, that's listed up here in the process. So let me highlight that for you. Second trace, and then you're looking for the one that says intersection, which is option 5. Second trace, option 5. All right, so again, that's second trace, and then select option 5, which is intersect. Once you select that, it asks you for the first curve, then it'll ask you for the second curve, and then it'll ask you for a guess. If you're looking at an intersection between just two functions, all you have to do is just hit enter 3 times. So hit enter, it'll ask for the second curve, at which point the blinking cursor will move to the second curve. So hit enter again, and then since there's only one intersection, the guess is irrelevant. If there was more than one, then what I would want to do is move my cursor as close as I could to the intersection itself. But in this case, it doesn't matter. So you can just hit enter a 3rd time. And it'll actually flat out just give you that intersection point. All right. So I know. I've been doing this long enough, as you know, 20 years. It's a convoluted approach. And you're like, what the hell? Why are we doing it this way? What is wrong with this guy? There's got to be an easier way. First thing I'll tell you is that really is the easy way. Because the alternative is doing it by hand. Now, I said before that doing it by hand in this one particular instance would be a little bit easier. But we're going to get to an example in a couple minutes where it's just not. That's just not how it's going to play out. All right. So we want to learn the process here so that we can apply it in other situations. Right. So I also just need to state the answer. It says determine the percent return if the percent new is 25. So percent return is whatever the intersection is, 22.8 approximately. All right, so the calculator is giving it to you. And like the idea of saying, me saying, you can do everything in the calculator without writing anything down except for the final answer. You look at it and say, well, yeah, but look what I got to do in the calculator. It gets easier with practice. All right, so you do have to actually do this on your own at some point. And this is a little caveat, so I don't mean to be so aggressive right now, but on the test, like you do have to demonstrate knowledge of the skill. So unfortunately, you can't ask me how to do it on the calculator, all right? Because that is the skill that you're being assessed on, all right? So it can't be like, oh, how do I get to the regression function again? I don't remember. Because the skill that's replacing is the required knowledge for the course, which is the solving it algebraically. So the new skill is what you're being assessed on, and that's the calculator usage. All right. So if I were to help you with that, that would be like if I were in an algebra class and you were presented with a problem that said solve for x, and I were to walk you through step by step how to solve it. All right. So it wouldn't be fair. All right. So I just wanted to say that now so that I don't have to say that to you during the test. All right. Because that gets a little uncomfortable.
Is there any rules for our notes? So we can write down on the steps?
Is there, say it again?
Is there any rule for our notes?
Oh, like for the test? Yeah, on the index card, yeah, you just gotta write small, but you can get it in there. Because I've found that over the years, the 3-inch by 5-inch index card is sufficient because you think that there's a lot of stuff to write down because you see all this stuff here, but it's really just second trace this and blah, blah, blah. I just have a lot of screenshots. Right, so it all ends up on there, and as you're creating your index card, you're going to find that the only things that you're writing on that index card are calculator steps. All right, the other conceptual stuff is not going to be necessary.
So all that is making prediction, right?
That's making a prediction of x if you know y.
Okay.
All right, so I'm about to show you how to find y if you know x, which is actually much, much easier.
Okay, would you mind going back to the beginning so I write down everything and other people who want to?
Like,
So we go second mode, stat, calculus, for frequent list, put all the numbers, right?
yeah.
Clear on the, let me see, frequent list.
Right, that should already be blank. But if it's not blank,
And
clear it out.
calculate,
And then
right?
calculate.
Then store.
Then once you hit calculate, it's already stored. And so when you create the graph, the line will come
No,
up.
I'm on the top, like store and
Oh,
then
store regression equation, yeah. That's alpha trace.
okay, alpha trace, then y1, enter, calculate, enter,
Yep.
then goes to y equals ax plus b, then ab, yeah, and then after that, second y, okay, second y, plot one, and type zoom 9, is that correct?
Yep.
Zoom 9, enter, then window, then
And we change the window so that it actually shows the horizontal line. That's the most important part because you have the y value of 25 that needs to appear.
yeah,
So once I go into a window and I see that y max isn't big enough, I need to make that bigger.
okay.
So I make
So
that adjustment.
26. Then
Thank
he
you, Brad.
graph window again,
Right, and that was because we saw that it, even though the horizontal line appeared, it wasn't crossing the diagonal line, so we wanted to make it go a little bit further to the left so that it would actually appear.
Then minimum, zero,
Minimum 0, then we hit graph,
graph, second trace,
option 5,
5.
and then
Then-
enter, enter, enter.
Okay, so to go to the intersection, do I use enter or the arrow?
Arrow to get to the intersection, and then enter, enter, enter.
Okay, so I couldn't get to the intersection, but I didn't want to start the class. What if it doesn't show intersection because of mine didn't?
Any question I give you
Mm.
will show an intersection. It has to, otherwise it's a bad question.
Okay, so
Someone told me we
Okay,
had
so you got it. Yeah, it's right there. So second, so you have an intersection, so second trace 5, and then enter, enter, enter. And then it says
okay, so 3 enter.
3 entries, yep.
Thank you.
No problem. So then the next part, determine the percent new if the percent return is 90. Much easier process. There's a few different ways of doing it, but I'm just going to obviously go to the easier way. And again, can't emphasize this enough. The ways that I'm showing you are the easy ways. All right, even though you look on the side there and you're like, how is that the easy way? That's the easy way, I promise you. All right, so I'm going to hit second mode. So I'm going to quit out. So second mode, I'll just jot down those steps here, because this is much simpler. So that gets you into the home screen. Then I'm going to hit alpha trace. And select Y1. And then in my home screen, I want to have it say Y1, open parentheses, type in the 90, close parentheses, and then hit enter. So alpha trace Y1, open paren, type the 90, close paren, hit enter. So alpha trace Y1. All right, so that gives us flat out the Y value for a known X. All right, so the percent return here is about 4.5. All right, so I'm sorry, the percent new is about 4.5, which I think kind of makes sense in the context of the situation, because if you have a particular colony and 90% of the birds that left are coming back, just in terms of space, that would not allow for an influx of new birds, a heavy influx. So the more of the original birds that return, the less new birds are going to come in. But if less of the original birds return, then maybe you would expect, because there's more room, more resources, more new birds to show up. All right, so it contextually seems to make sense. All right, but obviously one process is way easier than the other. Right, and that's just how it is. There are other ways to handle B, but I feel like if I start mixing concepts together, it's just going to be dangerous. Because there's a function in your calculator known as the solver. It's a useful function, but I feel like there's enough similarity with this that people are going to get confused. So I'm going to leave it there. But if you wanted to research that on your own, just look up solver on TI-84. There's plenty of videos and stuff like that that'll walk you through how to use it. Probably by me. All right, so an outlier. So this is just analysis of the data set, right? So an outlier is a data point that diverges greatly from the overall pattern, right? So anything that looks too far out of whack is going to be an outlier. Oh, sorry.
I got like a 2250. I don't understand what I'm doing wrong. No, that's really wrong.
You gotta cite the parentheses at 90.
What are the parentheses?
I was just sure.
Oh, 8 and 9.
So alpha
Oh,
trace,
8 and 9. Okay, so alpha trace.
wide open paren right there.
Well, this is it.
Yeah,
Okay.
there you go.
4.57. Okay.
All right, so any point that looks a little out of whack is going to be an outlier. All right. An influential point is a point that impacts the slope of the regression line. All right. So for that, there's a little bit more work involved, but it's not work that you're doing by hand. You're never really doing anything by hand. So let's put this new data set in because I just wanted to have something that didn't have any context, something relatively simple, and also something that may or may not clearly have an outlier. Right, so stat edit. We're going to clear out these data points. So 1, 2, 3, 5, 9, 11, 3, 5, 7, 10, 16, and 20. This might be the better way to go. So type in your data. We're gonna follow a lot of the same procedures that we did in the last question. So we'll develop a little muscle memory here. All right, so you're gonna hit stat, calc, option 4. You're gonna make sure that your settings are the way you want them, which is L1, L2, and then store regression equation. Again, we want to put that in Y1. It's unfortunate that it'll retain the settings for XList and YList, but not for store regression. So every time you do this function, you have to type in alpha, trace, Y1. All right, so alpha, trace, and then the Y1. And then calculate. So it gives us the regression equation. And we just want that on paper at some point. So just reiterating what I said before, I'm putting all these screenshots in the notes, but all this is happening behind the scenes. This is the first instance where you're actually writing anything down for this question. All right, you're writing down the linear regression equation in this form. So basically, like you're doing the closest that you can to an approximation of a screenshot of this outcome on your test. So when I say linear regression equation, you're reproducing this on paper. All right, with the idea being you're just demonstrating that you did all this stuff in the calculator behind the scenes. I'll know it because you got that. All right, it's kind of like an implied show all work. You know, if you write this down correctly, then I know that you did the work. there's credit in there. And also something to keep in mind: if you write this down in this form and the numbers are wrong, that's like a half a point deduction, because I know you did all this stuff to get to this. The reason these numbers would be incorrect is because you typed something incorrect here. And I'll tell you the number one error that happens on a test is that people just simply don't type the data in. So somebody, you know, a small enough group, and I'm emphasizing it, I'm hoping it doesn't happen. But every other year that I taught this semester that I taught this course, there would be a student that put this answer, this exact answer, to the question related to this topic on the test. They would hit stat, cal, for. They put all this stuff in beautifully, hit enter, and they got this. Why? They didn't put the data in for the problem on the test. They just had the data in from this. The calculator doesn't have like a QR code reader. It doesn't like look at the test for you and say, oh, okay, that's the data you want me to look at. You got to type it in first, right? But sometimes nerves get in the way, so just remind yourself of little things like that, right? I've had students that were so concerned with becoming a story for a future class that they were like asking me during tests, like, is it okay to do this? Is it okay to do that? I don't want to end up being a story. So please tell me, you know, that's fine. Okay, so we have our equation. Construct a scatter plot. All right. I've seen this before, and I think it's a great strategy where people, so second y equals, so it's the same menu, right? I saw on a student's index card, they drew this screen. And then they drew little lines. To the first one, scatter plot. To the third one, histogram. To the fourth and fifth one, box plot. And to the last one, normal probability plot. They actually drew out the different types on their index card as little reminders to themselves. Not something I would ever think to do for myself, but once I saw that, I'm like, yeah, if you're a first-time user of a calculator, that's a great idea. So by all means, right? Settings are exactly the way we want them. The last problem we did was a scatter plot. So is this one. So we're good to go. L1, L2, same. So zoom 9. Look at that. That's a good looking graph right there. Just hit zoom 9. Yeah, it'll overwrite the, just hit zoom again and then 9 again. It'll overwrite the previous problem. All right, so you can't have an influential point unless it's already an outlier, because part of the definition for influential point is an outlier that greatly affects blah, blah, blah. So an outlier is something that's out of whack. You know, it diverges from the general trend. Well, the overall pattern of the data is linear, and I don't see anything that's too far away from linear. All right, so I would say that there are no outliers. Or influential points.
But is a pattern is linear, so there's no outliers?
Yeah, exactly. Now, if you compare that to the previous question, you'd look at that and say, oh, I can make a case that maybe, you see you've got a couple of points down here. They're a little far away. These are what we would call possible outliers. Oh man, I keep getting that. Sorry.
A perfect plot, the linear plot as well?
It's very close to perfect, and I'm going to show you how to figure that out in a sec. I'm just trying to fix the display so that you could actually see what I'm writing on the right-hand side, because I keep forgetting that it gets cut off. All right. So this looks damn near perfect, but if you look closely, this one is, it's a box that's filled in, but these are, slightly off. So if I had to take a guess, I would be thinking that my R value is probably very, very close to 1, and my R squared value is very, very close to 1, but probably not exactly 1. All right? So what I would want to do is let the calculator figure out what the R squared value is to determine the type of fit. All right? So let's do that. So to find the R squared value, we need to make sure our diagnostics are off. So to find R squared, turn on stat diagnostic. It's in the mode menu. All right. Then recalculate the LSRL, which is, again, the least squares regression line, linear regression equation, line of best fit. It all means the same thing. But LSRL involves writing less stuff, so that's why we do that. All right. So let me walk you through that. So again, I probably brought this up too quickly. To find R squared, turn on the stat diagnostic, which is your mode menu, and then recalculate your least squared regression line. All right. So mode. This actual step here is a one-time deal. So if you do this now, you won't have to do it again unless you reset your calculator for some reason. So don't reset your calculator. So scroll down in your mode menu, and you'll see an option that says Stat Diagnostics. For whatever reason, the default is off. It should be on. So hit the right arrow to on, and then hit Enter. So then we can quit out of here, so second mode. So you'll never have to do that again. So just don't reset your calculator and you're fine. If you end up resetting your calculator, you'll have to do it again. Yeah, that doesn't matter. Yeah. So then we're going to do the stat calc 4 thing again. Stat calc 4. We're going to store the regression equation again, alpha trace y1. And again, it's one of those things, like you do it enough times, it becomes more familiar.
What did I do wrong?
You want to hit
the alpha trace? I did it.
So stat calc
I did that.
4.
Okay.
Then go to store regression equation, alpha trace y1,
Okay.
and then go to calculate and hit enter. And there it is. So then we're going to hit calculate, and it's going to give us the same display that we had before, just a little bit more. All right, so I'm going to hit enter, and we get this. And you're like, okay, cool. There's more stuff. So not only do you get the A and B, but now you get the R squared and the R. We're very concerned with the A and B, obviously, but we also would like to know about the R squared. All right? And that's based on that table that I had you write out on the, what is it, 2 pages ago? All right, just talking, maybe it was the last one. But it's talking about the percent of variation that can be explained by one variable imposing its effect on the other variable. All right, so this is very close to a 100% effect. All right, so that's telling me that the two data sets are really in lockstep with one another, or as close to lockstep as one would expect. All right. So my r squared tells us that 99.7% of variation in y can be explained by variation in x. All right. So that's the example that I was talking about before with the height and weight. So person grows by 1 foot. All right. And that corresponded to a 20-pound increase in weight. What this is saying is 99% of those 20 pounds, that change in weight, was because of the change in height. All right? That's a meaningful piece of information. So that person doesn't really need to be concerned about diet, exercise, and stuff like that. The gain in weight is strictly related to the change in height. All right? Now, if I got something like 10%, that would be that 1 foot of growth only accounted for 10% of the change in weight. So out of those 20 pounds, only 2 of those pounds came from the height change. The other 18 pounds came from something else. What would be the something else? Those are the lurking variables. You start thinking about diet, exercise, maybe other health concerns, things like that. All right, and so this is an incredibly important number. It's beyond the scope of what the question is asking, but it's very, very meaningful because you can take, just like the recurring theme in the course, I want you to be able to take a concept out of the classroom on any given day and apply it immediately. This is something that you could apply immediately. All right, it's very, very interesting stuff too. On top of it, pretty rare. You get something that you could apply, and it's also meaningful. We're going to skip this topic, at least in this unit. Actually, what time is it? Yeah, we're going to call the unit